Assalamu alaikum and hello everybody. Welcome to the 31st Distinguished Lecture Series organized by the Faculty of Engineering, University Technology Malaysia, UTM. My name is Nick Rumsey and I'm the Head of Power Electronics and Drives Research Group, School of Electrical Engineering. Today we are very honored to have our guest speaker, Professor Taufik from California Polytechnic State University, or Cal Poly, in San Luis Obispo, California. Today he's going to talk about one of his interesting projects on DC House. The title of his lecture is the DC House Progress, Challenges and Opportunities. Actually, Prof. Taufik is not new to the Power Electronics and Drives Research Group because he was here, I think, in 2008 to give a tutorial on DC-DC power converters. And today we are very delighted to be able to meet him again here in cyberspace. Without further delay, I would like to now pass the session to Prof. Rafiq, our Dean of Engineering, to introduce you to Prof. Taufik.
Thank you, Professor Nick Rumsey. Assalamualaikum warahmatullahi wabarakatuh. And a very warm welcome to all of you. Welcome to our 31st UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq, and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Taufik from California Polytechnic State University, USA. A bit about our presenter today. Professor Taufik received his BS in Electrical Engineering with minor in Computer Science from Northern Arizona University, MS in Electrical Engineering from University of Illinois, Chicago, and Doctor of Engineering from Cleveland State University. He joined the Electrical Engineering Department at Cal Poly State University in 1999, where he is currently a tenured full professor and the Director of Electric Power Institute. He received numerous teaching awards, most notably the 2012 Outstanding Teaching Award from the American Society of Engineering Education, Pacific Southwest Section. He is a senior member of IEEE and has industry experience with several companies, including Capstone Microturbine, Rockwell Automation, Picker International, San Diego Gas and Electric, APD Semiconductor, Diodes Inc, Enerpro, Renewable Power Conversion, and Sempra Energy. His areas of research include power electronics, power systems, rural electrification, energy harvesting, renewable energy, and smart grid. He has published over 200 technical papers in journals, reports, books, course readers, and served on the editorial review boards of several journals. So that is a brief biography of our distinguished speaker today. Here now is Professor Taufik from California Polytechnic State University, USA, with a talk on the DC House project, progress, challenges, and opportunities. Professor Taufik, over to you.
All right. Thank you, Professor Rafiq and Professor Nick, for the very nice introduction. I really appreciate it. Most of all, it is a pleasure to be back meeting you folks from UTM. I really appreciate it. It's been a while since I met with you or visited UTM, and it is long overdue. And I need to someday go there and visit you guys again. But I really like to again thank you for the opportunity for sharing this research that is very near and dear to me, which I started in 2010. So it's been 10 years running into this research, and definitely a lot of challenges and opportunities. And this is something that I would like to share with the rest of academia, and with the hope that hopefully we can become partners or collaborators on this effort. And so right there is the title of my presentation, the DC House Project, Progress, Challenges, and Opportunities. Again, my name is Taufik. I've been teaching at Cal Poly for 20 years, going into 21 years. And I'm also the director of Electric Power Institute at Cal Poly. And so before I go into the research, I always have these 2 slides just to introduce you to the school itself. Just briefly, it is a school located in California, located in between LA and San Francisco. So it's very strategically located between the 2 industrial-based regions, and very beautiful place to visit. Originally, this campus was named California Polytechnic, which is a polytechnic school, and then later on it evolved into a university in 1972. It is part of the 23 university, Cal State University campuses, and it is very highly competitive university to get into. That's the last statistics I have right there, where the first-time freshman students average high school GPA is 4.04 out of 4. If you're wondering how come the GPA is over 4, if you've been in the US, you know why. It's actually because many high school students, they take honor AP classes or honor classes where if they get an A, they get a 5.0 out of 4. So basically, people who are applying to Cal Poly are, people who have, or students who have pretty high GPA. Our population is about 22,000 students, 6 colleges so far, with engineering being the largest, with more than 5,000 students. And our philosophy is learn by doing, which means, it's just a lot of labs. That flavor of Polytechnic still very, thick in our school. Again, originally it was a Polytechnic school before it converted into a university, and so we still keep that learn by doing flavor. So a lot of labs. There's the picture of the campus. In the beautiful scenery of San Luis Obispo. I cordially invite you to visit the campus one day. That yellow arrow right there, that points to my little office on campus. So hopefully Professor Rafiq and Professor Naik, if you have time in the future, if you get a chance, I'll be waiting in there, and hopefully you can come visit us. Right? So far, I've hosted a few people from, or scholars around the world to actually do research at Cal Poly. We have 6 PhD students. We've had 6 PhD students from Indonesia in the past. We also have 1 PhD student from Malaysia, by the way. I think he's from Tan Hussein on University. 2 undergrad students from Thailand, 3 undergrad students from Philippines, and another one, Fulbright scholar from Indonesia. So please come visit, and I'll take you around. And as you can see from the previous slide, it's very close to Silicon Valley as well, very close to the beach. And so if you want to enjoy the beach, it's only 15 minutes away. You want to look at all these top companies in the world, it's not too far from our place as well. All right, that's enough about Cal Poly. Let's go into my presentation today. The outline will be, I'm going to go through the background and motivations, and then I'll explain what DC House is, and then I'll go into components of DC House, recent status, challenges, opportunities, and then I'm going to close it with a summary. All right, so about 2009-ish, that was the first time my background is in power electronics, as I said earlier, and then specifically my focus is on DC to DC converters. That was the main reason why back in 2009-ish, I was looking at different articles and noticed that there are some upcoming technologies back then related to DC, which I believe is going to be basically exploding. And based on that, I was thinking, maybe it is time for us to rejuvenate, the DC technology. If you read the history between AC and DC electricity, you learn that DC electricity is not new. It was introduced by Edison, but then you got basically Tesla and Westinghouse now becomes the most dominant electrical system in the world. But then it doesn't mean that we should be just forget about DC. I think with this upcoming technology with DC, we should be able to somehow leverage the technologies and complement the existing electrical systems with DC. So I'm just going to mention two technologies back then that I believe was going to be growing fast, and indeed they have. The first one was smartphones, right? Or back then there was no smartphones; it's just a cell phone. And then I realized that wow, a cell phone back then, I was sure that that people who will be using cell phones will be growing and growing every year, right? And it would become more affordable year after years. And so I was thinking, as an electrical engineer, right away I'm thinking about energy usage, right? So if let's say that if you look at that picture on the left right here, right, that's actually the number of smartphones being shipped globally. You can see that about 2020, we have around almost 2 billion smartphones in the world. Now, just you doing some rough calculation on this, very conservative calculation, very low number. Let's say that every single one of these smartphones is being charged by USB, which has around 5-volt voltage and 1 amp charging current. And let's say that it takes 1 hour to charge, and then times 2 billion numbers of smartphones. You can just do this math, simply in your head, and you can see that that's a big number of energy being used by a smartphone, right? So that's the amount of energy that we are currently using. Not a small number. Yes, it is small if you just look at one smartphone, but when you multiply that by 2 billion, that's not going to be small anymore, right? So as an electrical engineer, I was back then, I was thinking, there should be a way for us to be able to somehow, again, leverage this technology, right, for future electrical systems to make it more energy saving, so lower the cost of energy usage. And then the other technology that I was observing that would take off was light bulb, right, the DC light bulb. And you can see that it really that technology took off around 2012, 2013, 2014. You can see the exponential curve. And back then I was like, man, if every single light bulb in a house is being replaced by LED, imagine how much energy, how much DC energy every house will be using, just like the smartphones. So it's going to be more and more households using more and more DC energy. So that's the reason why I thought maybe I should do something here. I should start a project where I could somehow, make use of these, utilize these, DC technologies. And I'm not gonna talk about tablets. It's the same thing, even though the growth kind of plateau a little bit, but it's the same kind of story. So then another thing that just came out recently, right? I say recently, it's actually 5 years ago. It's a USBC, and we all know what a USBC is, right? It's a different type of USB, and this was unveiled by Intel in 2015. The one feature that I really was kind of amazed to see, I was jumped out when I look at this feature, is that this USB-C can actually handle, or plan to be able to handle, not quite there yet, but supposedly the target is that this USB-C eventually would be able to handle 100 watts of power. And of course, this is going to be DC, not AC, because as we know, USB is running DC. And it's not going to be 5 volt, it's going to be around 19 to 20 volts. So higher voltage to keep the current low. And here is the feature, the different features of a USB-C, right? And You can see that eventually it can handle up to 100 watts. And imagine, right, if a USB-C can handle 100 watts, think about how many electrical loads in the house that can be powered by USB-C, right? Laptop, for example, now eventually could be charged straight from DC bus. If we have a DC bus in the house, like a laptop typically charge around 60 watts. TVs, whatever it is, LED lights, right? All can be powered through USB, right? So that's again another thing that we're seeing is going to be increasing, in future, near future for DC technologies. So all of these really amount to my projection of an increase in DC loads, which is again the reason why I chose to develop the DC house system. Right? I've done this study. I can't recall when, 2010 maybe, I don't remember, but you can see on the left. Actually, no, this is recently, 2018, I believe I did this. In year 2000, this is in the US. A typical residential house in the US would have about 20% of the house operating DC, meaning DC loads comprise 20% of the residential load back in 2000. And then in 2018, that number increases to around 30%. Right? And you can see in year 2000, we have TV, we have laptop, we have desktop that can actually run from DC electricity. Whereas nowadays we have more than just those three, right? In addition to TVs, laptop, and desktop, we also have smartphones, tablet. Nowadays we have also LED lights and LED TVs, right? So the number is growing. As you can see, that the percentage of DC loads in residential house is growing. Again, this is in the US, and I'll bet you that in third world countries, as well as rural areas, this number is actually bigger than 30%, right? And as you see from this arrow, this number is going to keep growing as the year goes by, right? So that's one thing that I observed. So then what is the big deal about this? Well, as an electrical engineer, I know that currently our house is being supplied by utilities, and they are supplying AC, right? Mainly AC through the wall plug or wall socket. Right? So in order for us to charge our DC loads, such as a smartphone, for example, you're going to have to use either a converter. We call it a converter. Technically, we call it converter, but people call it adapter, which is basically just a device that converts AC to DC, right? So what is the problem with that? Here's again just a simple math calculation that really blew me away when I look at this simple calculation. Let's say that we are still doing this, right? AC wall outlet using adapter to charge our cell phone. I'm just going to use two examples, charging a tablet and charging a smartphone. Now, a tablet, based on the article that I read, consumes about, on average, 12 kilowatt hour per year. That's in 2016. And in 2016, there were also 760 million tablets around the world, right? Now, if this converter, right, is very efficient, meaning there is no loss, then that's fine. But the problem is, just like any other systems in the world, it will have some loss of energy. When it processes the energy from AC to DC, it will have some loss. So I'm going to take a very conservative value of 5%, right? So given, for example, 760 million tablets in 2016, each one consuming 12 kilowatt hour per year, and you can calculate that that would result in about 480 gigawatt hour per year of loss. So what I colored there in yellow, that's the loss, assuming 5% loss. Now, if I do another example, a smartphone. In 2019, there are 2.71 billions of them, and they take up about 4.2 kilowatt hour per year, right? You do the math there, and then if, again, I'm assuming 5% loss on the adapter to charge these cell phones, then that would represent about 599 gigawatt hour per year. Not a small number, is it? So therefore, if you combine the two numbers, just from the two DC loads, right? Just from tablet and smartphones, if you add those two losses, you can see that the total amounts to about, or equivalent to, 12 units of 10 megawatt power plants operating 24 by 7 for the entire year. And that's a lot of energy, right, to lose. So that's why it is a big deal for us, especially for EEs, for people who have my background, to be able to improve this, right? So that's motivation number one, is that if you have a main DC bus instead of an AC bus in our house, this would be more efficient than having the what we are having now, right? So if you could somehow have a new type of technology where we have a main DC bus in our house, that would be more efficient than living it the way we have nowadays, where you have a AC bus converted to DC, and then you have another DC to DC to power our loads, right? So that's one motivation, is to save energy. The second motivation I have for this project is that we always hear this news about the increasing use of renewable energy, in particular PVs, right, or solar panels, or rooftop solar panels, to be more specific. Right? In California, we're seeing more and more people are putting solar panels on their rooftops, and as you can see, the global market of rooftop solar panels is steadily increasing, right? And if you know the electrical systems behind solar panels, you know that they are actually running DC. So they're outputting DC, right? So imagine these solar panels on the rooftop. It just means that every single house will actually have a DC source right on their home, right? So we already have a DC source in terms of solar panels. And then we have DC loads in our house. And so logically, right, if you have a DC source and a DC load, you should have a DC to DC converter. Instead of, right, if we keep doing the same thing as we're doing today, right, you have a DC source, which is our PV, you convert it into AC because our wall plug is AC, and then you power DC loads through a DC to DC converters. You can see there are two stages here instead of one. So definitely, if you do the first method, it would be more efficient than the second one. And from the article that I read, if you go from DC to AC, the first conversion right there, the loss is about 23 to 28%, not a small loss. And then from AC to DC right here, so actually, I'm sorry, from PV to AC is 23 to 28%, and from AC to DC itself, so from here to here, that's 17 to 35% loss. So you can see a big amount of loss. And really, we should not be doing this, right? In the future, when electricity demand is higher, is increasing, if we keep doing the same thing, then we're just going to lose a lot of energy, right? And you, as a customer, we actually paying for that loss. So that's the second motivation. The third one is opportunity to help others, right? We are, as a human race, we accomplish so much these days, but yet around 1+ billion people in the world still living without electricity, mostly in our brothers and sisters living in remote areas, right, or geographically hard to reach by electric grid. So even though the electric grid is not far, but it is not economically viable to support them, right, because of the whatever reasons, maybe not too many populations, what have you. So we are still having people living in these different areas without any electricity. So it'd be nice as an engineer to be able to contribute, right, to these to help these people. So that's another motivation. And I like to show this because it shows both actually Malaysia and Indonesia. You can see that the main region of Malaysia, right, is pretty lit up. Same thing with Indonesia, which is the Java Island. It's already lit up. But if you look at the part of Malaysia in Borneo, right, northern Borneo, some, but not, you can see some of other regions are still not lit up. And especially in Indonesia, if you look at the eastern part of Indonesia, still dark. So I like to help in any way I can, right? So providing electricity, that would be the opportunity to help others, making their life easier. I grew up using kerosene lamps, and so I remember how uneasy it is, unhealthy it is to use kerosene lights, right? So anything that we can help, right? So even if I put smiles on one of these children, that would definitely give me the big reward in doing this project. So that's, to me, that's also a very important motivation. So then what is the DC House project? And it started in 2010, a project to develop, initially, it is a project to develop a residential DC electrical systems for rural electrification and remote areas that would enable the use of DC electrical loads directly and seamlessly from one or more small-scale renewable energy sources. So that's what it is. And to ensure that this electricity can be safely and conveniently accessed in homes, eliminating the wasteful conversion of AC to DC, and in many cases, DC to AC prior to entering the home. And I'm not going to take credits in terms of the DC electricity itself. I mentioned earlier, there are other efforts, previous efforts to doing this. I'm expanding the effort. I'm extending it as well to be more comprehensive, to have a more comprehensive approach where the system will be scalable, reliable, flexible, expandable, affordable, and utilizing small scale, not big scale, small scale renewable energy sources. And so to me, a DC house is really a concept more so than a system, right? On a smaller scale, a DC house system could be a solar lighting box. Imagine if you have a box. If let's say you design a box where you have a small battery and LED light, where this kid during the day would put it under the sun, right? Charge the battery, and at night, they would bring the box inside the house and turn on the switch, and they have a light instead of a kerosene lamp. So that could be a DC house system, quote unquote, as a concept. On a residential scale, a DC house system is a standalone off-the-grid house. On a bigger scale, it could be a network of DC houses. So again, it's a concept. I'm going to skip through this. These are all the benefits of DC house: reliable, scalable, multiple, expandable, reachable, and flexible. So all these benefits we should be able to get if we are able to develop the proper DC house system, right? And I want to go into this block diagram. This is the simplified block diagram of a DC house on the residential scale. So there are three different groups. The first one on the left is the generation side that consists of small DC sources. So this is one different feature of DC house, right? Is that it doesn't require a big centralized system. It could be small systems like this, and it could be multiple. It doesn't have to be one. It could be multiple of those, along with their power conditioning converters. And then we have the interface plus the bus. So in order for us to be able to obtain this energy, I would have to have a way to combine these energies from these multiple sources and put it into a single DC bus. That's why I call this box MISO, which is a name of the Japanese soup, but it actually stands for multiple input, single output converter. A converter that is able to take in multiple inputs and output into a single bus, right? And that is the second stage or second group of the research. And then the last part of the system would be the load itself, which would be the house. with all of these DC loads. Right. So what have we been doing with this DC house project? A lot since 2010. If you remember those three different groups, okay, generation, interface, and load, we try to do at Cal Poly and my partners at different schools in the Philippines and Malaysia and Indonesia. We try to develop these three different part of the systems. The first one on the generation side. Again, remember that DC house does not require a big source, only a small low power source. So therefore, we're trying to think of different ways of generating power, small enough, but enough to provide some energy into the house, such as to light a LED light bulb, right? And so one of the things that we've done, for example, we try to develop what we call play park generators. It's not our ideas. Somebody's done it before. So we just trying to leverage the technology again. So for example, you see from this picture, we have a merry-go-round generator that will give us DC power, which actually worked. And then we also have the swing. We actually did this and also worked. It was able to charge a cell phone, for example. And we have a what do you call it? Seesaw. This is a hard one for us because we're not mechanical engineers. So if there's mechanical engineers out there interested in this type of projects, you're welcome to do this to develop this system. Another thing is we want to have a low-speed generator for these sources. So instead of developing new generators, we like to actually reassemble or rewind alternators from used cars. So we tried that, and we were able to lower the speed to about 600-ish RPM from car alternators. We need lower than that, and we need help on these as well. This picture right here with a hand on it, that was an idea that I had, but since I'm not a mechanical engineer, somebody in Europe beat me to it. The idea was to have a handheld hydro generator as well as wind generator that you can just bring everywhere, anywhere. And as long as you see a stream of water, you would drop it in the water and it will produce enough energy to charge, for example, a smartphone, right? That can go into, or battery that can go into your house. And so I tried and I failed. And so it was a good try. But then I found that somebody in Europe already actually made this several years ago. In fact, if you go to Amazon.com, they're already selling this product. So again, that's not the only version out there. You can actually produce different version of that type of technology. In terms of the second group, which is the interface and the DC bus technologies, the MISO itself, it sounds like, if you look at the picture, it looks like it may not be bad to do, but it's actually very difficult to do. And so we tried several times, and finally we were successful in developing a new multiple input single output DC to DC converter. And myself and my student actually received the US patent just last year for this technology. And that's the picture of that multiple input single output that we developed at Cal Poly. Another component in that group would be the energy management system. A lot of controls going into here. Not really my cup of tea, so I really need help on this. If you're interested in, intelligent controls of energy management systems, be my guest. I'll be more than happy to discuss the requirements with you. Right. On the load side, this is one that's I'm most interested in. The problem with DC is that the loads are not standardized, unlike AC. AC, everything is 120 volts in the US, or 220 in Indonesia, or maybe in Malaysia too. So they are standardized, right? So you can just buy any equipment, AC equipment, and you can just plug into the wall. DC is not the case because DC loads varies in terms of the requirement. Smartphones, for example, if you want to charge it, has to be 5 volts. A TV could be 12 volts, could be 24 volts. and there's a DC refrigerator that can run in 24 volt. Bottom line is they run different voltages. So I think it would not be wise to have multiple wall plugs, DC wall plugs in the house, right? So the smart way to do is to have just one DC plug, where the DC plug is smart enough to figure out what DC load is required, right? What DC voltage is required by the load. And so that is the idea behind smart wall plug. And here's a picture of a smart wall plug that we developed at Cal Poly. You know, it worked, but it would still need a lot of improvement, definitely. But it works, right? So you can plug in any load with any voltage, and this converter is smart enough to figure out, hey, I need 12 volts. Hey, I need 5 volts, and so on and so forth. The DC light bulb right there is more than just a light bulb. It's actually running at 48 volts. I know that we can now buy LED lights, but this is straight from DC, and it's high voltage, 48, considerably, relatively speaking, you know, high voltage, because most of the DC light LED today is 12 volts, but we want it to be 48 volts. The reason being that the DC bus that we are using is 48 volts. And then USB-C plug right there. We also developed that at Cal Poly. Again, this is to be able to be ready when USB-C can actually achieve higher power. Remember, we talked about USB-C earlier that can handle 100 watts. So I want to be prepared when that time, comes. And then the protection of the DC is not an easy thing as well. It's not like AC where the waveform, crosses the zero twice in a cycle. But in the DC, the signal does not cross 0 volt at all. So it imposes technical challenges for us to protect it. And so we come up with 2 different technologies here. The first one is solid state DC breaker and DC fault interrupter. And any one of these is a presentation by itself. I could definitely spend 1 hour just to present these technologies. So maybe for future discussion. And so the next step that we've done also is having prototypes will be useful. So it's not just as individual experiments here and there. It'll be nice to actually assemble everything together, right, and see how the system works with these different components in the system. And so we have one, for example, at Cal Poly. Right, there's the picture, which is not as nice. If you look at, very fortunate to have a friend at Universitas Pajajaran. His name happens to be almost the same as mine. His name is Muhammad Taufik, and he was very nice to offer, to build this DC house close to their campus in West Java. So very nice DC house right there. That's in West Java, Indonesia. Not far from there, there is Regency office, and then they collaborate with Universitas Pajajaran in Jatinangor, West Java, and we're able to put a small DC house system. You can see on the left picture, and there's him right there. That's Muhammad Taufik, and we were able to successfully install around 150 watt solar panel combined with around 250 watt wind turbine into the MISO converter and run some loads in this office. It was a big ceremony. I can tell you that story maybe when we meet someday. But yeah, right now I don't have time to do that. But it was quite an interesting story behind this installation of DC house. And I'm also very fortunate to have friends in Philippines who was also interested in having DC house on their campus. So there's the DC house on Technological Institute of the Philippines. I was actually there. I spent almost 1 month in Quezon City, Philippines, to actually help them put together the system. As you can see, a very nice traditional house in the Philippines that they have. This is on their campus, by the way. So they want to have this as a living lab for their students. So very nice house. And then we also have a project close to our campus here. This is a real off the grid community, and one of the house owners, they're interested in having a DC house system for her house. So therefore, we are currently putting together the DC house system for the house, as you can see from the picture. In terms of cost, really cost depends on wattage, different things, battery size, location, countries, and so on and so forth. But in terms of installation cost, we've done study. This is based in the US, of course. The AC to DC installation cost ratio is about 1.25 in the US, meaning that the AC is going to be 25% more expensive than the DC system. And then operating cost always favors, in my opinion, favors DC to its more efficient system, so therefore less losses, less costly. Maintenance cost is going to be comparable because both AC and DC systems would require the use of a battery if it's off the grid, of course. Right. And here's an example of one of the business models that we have tried in Indonesia, for example. This is old numbers. I don't think it's going to be the same numbers anymore. We sell this DC house system as a package. So we have two different packages, 150 watt package and 300 watt package. 350 watts comes with different components. 300 watts comes with more components. And of course, the price is going to be higher on the 300 watts compared to the 150 watts. So this is just an example. Challenges, oh my God, a lot. So it's a huge undertaking, right? If you go from the research phase to the adoption, so many challenges, right? I'm not gonna go through every single one, but definitely in terms of adoption, on the far right there, we do need a lot of support. Especially, it'll be nice if something like this receive some support from local government, right? If, for example, if let's say Indonesian government has a program on electrification of certain areas, certain islands, for example, then it'd be nice if you could somehow be tied into that project and adopt the technology, right? Same thing with product development here, trying to get partners, industry partners or university partners that can actually help build the products. That'll be nice, right? But that's still a challenge. Prototyping right here on the third one in the middle. Yeah, requires a lot of collaborations, right? International partnership is a must, because when we do prototyping, we want to make sure that the DCL system can be applicable to different type of environment, different countries with different rules, with different policies, and so on and so forth, right? And even on the research side and development side, since there are so many aspects of the DCL system that is not explored yet, therefore, we're going to need a lot of help from different students and faculty around the globe to participate in this project. So a lot of opportunities. Speaking of opportunities, still a lot more to explore. If we are pretty much done with a single house system, it'll be nice if you could somehow network this system, right, to improve redundancy. This is an example. Our current rural electrification typically follows the left picture. That's the model where we have centralized source, and then we have power being distributed into different houses. So then what happens if the source breaks? Then everybody's going to be having blackout, right? Or if one of these, let's say that this main line breaks, then of course everybody's going to have a blackout, right? And so on and so forth. So it's not quite reliable system. But if you have the system on the right, this is what I'm proposing, is that if every single one is a DC house, right, system, then you can see that we have bidirectional flow. And if this line breaks, for example, then all the homes, all the houses would still be able to have lights, right, electricity being supported by neighboring house. Again, assuming that, of course, we have enough energy to support. So it's improved reliability, right? Improved resiliency, and then the scalability also is better than the one system on the left. So that's my next project. this slide, I'm just going to show it quickly. I'm actually participating in a project in the US where we want to develop a low carbon or help create a low carbon society by building a low carbon house. And a lot of these systems that they're planning to do actually aligns well with DC house system that we've already developed at Cal Poly. I'm actually planning to present this later this month. There is a conference at the end of this month hosted by Universitas Brawijaya in Malang, and I'm going to be talking more about this slide. So again, this is a slide, this is a presentation by itself. Sorry, a lot of new technologies here too. A lot of interesting new technologies. So if you can join us at the end of this month, if I see you there, then I'll talk more about that technology. Opportunities as well, low-income housing, disaster relief shelters, right? So we can actually incorporate DCL system into those small houses for low-income community, for example, or disaster relief houses, including COVID-19. Right. Currently, I'm working with a university in Indonesia to actually get a grant from the government, Indonesian government, to actually do a DC house-based COVID-19, what do you call it, shelter, especially for areas away from the grid, right? So that's where this becomes very useful. And sky is the limit in terms of generators or generations. The picture on the left, right, that's a small-scale hydropower generator that was designed by a Japanese, I believe, a Japanese engineer. So that's just a different version of the handheld generator that I showed you earlier. On the right picture, you see the wind turbine, handheld as well, or something that you can carry around, basically. Right, so a lot of things to do there. And DC appliances, a lot to develop here. Again, it's a huge undertaking, as I said earlier. So many things to develop. So I won't be able to go through this every single one, but think about USB-C powered appliances, right? Your DC refrigerator in the future can be powered from a USB or DC TV, right? Or charging cell phones directly from a DC bus in your home, right? So on and so forth. All right, so that brings us to this another opportunity, future houses, right? So I envision that in the future, urban areas, even though this is initially for rural areas and remote areas, but a lot of questions came up during my presentation in the past about DC house. How can we adopt this into urban areas? And to me, it seems like the most logical way is to complement AC with our DC house system. So basically, in the future, I envision that residential house in urban areas would have two different electrical systems running in their house, AC and DC. So AC would, the AC bus would definitely power the big loads, right? For example, washing machines, big refrigerator, air conditioning, and so on and so forth. Whereas the DC load will be powering LED lights, chargers, or cell phones, and so on and so forth. The TV, for example, or fan, right? So that's what I would envision it to be, as well as smart home, right? Because basically all of these sensors and monitoring systems, microprocessors, these are all running DC. So if you have the DC bus already in the house, then going or having all of these sensors and smart controls will be seamless. You can just connect it to this DC bus without having to have a different conversion again from AC to DC. Right? So that is how we can prepare for future houses by using something like this, DC house technology. So in summary, I know I'm going fast because of the time. DC house as a concept that enables us to leverage DC technologies. It's an ever-evolving technology, started as a rural remote areas electrification, later on into low voltage DC grid, urban hybrid houses, smart home, disaster relief shelters, so on and so forth. So a lot to expand from the initial idea. And then this electricity is making a big comeback. That is actually the basis of this project, is to leverage the DC technology, presents opportunities for developing more DC technologies, helps leverage distributed generation utilizing PVs and small-scale renewable energies. And DC House offers an alternative solution to remote areas. I'm not saying this is the only solution, of course. This could be an alternative solution whenever appropriate, whenever suitable to use. Right? Why not? Right? More needed research, studies, and developments for different components of DC House. We need more international partners for sure for adoption of DC House system technologies. And hopefully, I'm hoping UTM will be interested so we can collaborate on this effort as well. And if people out there listening to these videos, if you are interested in collaborating on this effort as well, please do not hesitate to contact me. These are different references I use for DC House, and there is my contact info. And with that, again, thank you for the opportunity, and that would conclude my presentation. Thank you.
Thank you very much, Prof. Taufik, for the very interesting talk. And by the way, thank you for your kind invitation. We will certainly would like to look forward visiting Cal Poly someday if we have the opportunity. Yeah, I see a lot of opportunities for collaborations there from your project, from your presentation just now. And I was amazed to see the huge losses that we have. We have every day, especially with our mobile devices and so on. And to the audience, if you have any questions, you can now post your questions to the Facebook page, our Facebook page, and we will certainly be happy to entertain your questions. If you have any questions, please do it now. And while we're waiting for the question, maybe I can ask you, a question or two.
Sure.
Your DC house there, you're using a voltage of what is it, 48 volts for the distribution?
Yeah.
Yeah. Is it any reason for that, or why don't you use higher voltage, or for a particular reason? Yeah.
Yeah. So yeah, there is a reason. So back in 2011, I believe I have two different student groups independently working, so they don't know each other, and they're doing the same task, which is to research into what would be the most optimum level for DC voltage for residential scale, right? And so very first thing that we noted is that there is a threshold where above which there are standards that we have to follow, but below which there were still no standards. So we want to have freedom in designing our DC house system. So if you go above 90 volts, I believe, then we have to follow certain standards. So that would limit our, in terms of exploring more technologies. It will limit our ability to explore more technologies if there are already standards limiting the operation of that voltage. So that's why we picked below 90 volts as the start. But then for below 90 volts, what voltage should we use, right? Should we choose? So again, as I said, back in 2011, I asked two different groups, and interestingly enough, they both came up with 48 volts. Actually, they came up with between 42 and 50, I believe. But then I'm thinking, if a battery is about 12 volts per, voltage per battery, then 48 would be nice, because then you just multiply that by 4 to give you 48, right? So that's basically the main reason. So they came up with the different reasons for 48 in terms of efficiency, cable size, cost. I can't recall what else, but a lot of parameters they looked at, and they both came up with, basically 48. We converge into 48. And interestingly enough as well, today, if you look at the new DC standard, DC voltage, low voltage DC standard, or low DC voltage standard, interesting enough that 48 volt is actually the voltage that we are operating, right? So it aligns well with our previous study, right? What industry has converged happens to agree with our previous study back in 2011. So we are glad that we picked 48 volt.
Yeah, that's a good choice. Prof. Taufik, can you close your PowerPoint window?
Okay.
All right. Okay, I believe we have a question here in from Mas Effendi in Indonesia. Maybe I can translate it to the audience. Obviously, we can understand, but some people will not be able to do that. He said that he just knew that the losses is basically their pakai converter ada loss. Yeah, he just realized that the converter there's a loss in the converter as a heat. Is there any other losses other than that? Something like that.
Yeah, I mean, mostly comes from power flow, so mostly comes from heat. I'm guessing this is a converter for the DC, maybe. So in terms of the DC technology, yes, even though it is more efficient, but of course, we cannot avoid having losses, mostly from power flow, current flowing through a lossy device. But in addition to that, what we need to also be aware of is the noise, right? And this noise could create more losses because they're switching, right? They're turning on and off, on and off. So if you don't take care of these EMI, as an example, noise, then you can have this noise coupled to another circuit and creates more loss. So, but I think the majority of loss, definitely comes from power flow. Power loss or heat.
Do you have any special design on the converter in order to minimize the loss? Any
So one of the things that I mentioned that there was one PhD student from Malaysia, from is it UTHM? Is it? I don't remember.
Yes, that's right. Yeah, UTHM. Yeah.
And his research was actually on that, using different topology. That's one way, right? Using different topology to suppress losses. That's one. Also, nowadays we have better devices, right? GaN, for example, even though maybe this is not on the level of GaN, but why not though? If they're more efficient, right? We increase switching frequencies while using, for example, zero switching technology and things like that. So those are different approaches. However, there's another approach that comes from the EMI reduction level. That's another presentation by itself. But one thing that we that we have just looked recently at Cal Poly is this technology called SSFM, spread spectrum frequency modulation. So that's one way to suppress EMI to go back to the DC bus, because that's one disadvantage of using DC technology is that you might have some kind of harmonics on the DC, harmonic noise on the DC bus. So how do you suppress that? You have to be able to reduce EMI noise. And again, different technologies, you can do filter, EMI filter, you can do shielding, and you can do SSFM. And that's what we are actually, like I said, just looked into recently. It's the SSFM. So if you're interested, you can look it up, spread spectrum frequency modulation or reducing noise.
Yeah. And we have another question here, I think from Justin Gregg. Great presentation, Professor Taufik. I wonder what our electrical grid would look like if we knew before just how many DC loads and sources we would have now.
Justin, how are you? I recognize the name. This is my former student.
All right. Okay.
So he knows that I'm a big supporter of DC. So if we were to go back in time, I'm more in favor of DC. Why? Because it's less headache.
Yeah.
You don't have these, coupling effect, reactive effect. Don't have power factor effect, right? Yes, you have this noise effect, but comparing the two, right? I think that DC technology would, to me at least, is more superior than AC. But if you were again to go back in time, like Justin is asking, I would say, I would be a big, supporter of the DC transmission lines, right? Assuming that the DC technology was there. But right now we know it was not. So unfortunately, it's a bit too late to change AC to DC. So we don't want to do that. We want to complement AC with our DC technology. So yeah.
It's very difficult if you don't have power electronics, for DC transmission. All right. Maybe another. We have another question here. Maybe what obstacles are faced with the applications of DC house? Yeah, that's a question from Fazir Ilyas. Yeah, from Universitas Khairun.
Okay, thank you. If you met adoption, really is a big challenge, right? It really is what do you call it? A team effort. It's not even a team, more than team effort, right? You have to involve different components to be able to adopt this technology, right? I mentioned earlier about, especially in third world countries, right? You have to be able to partner with local governments, right? Being able to, be able to implement the DC house technology without, without having any conflict with the local culture and things like that. And so really, when it comes to adoption, I would say the challenge would be non-technical. The technical, of course, is a lot of challenges as well, but when it comes to actually implementing the technology, that's when we need our partners in the local country, locally in different countries, right? Local governments, local universities. Otherwise, I would not be able to do this. Right? I'm not sure that's the question though, because he's asking about implementing. So I'm guessing that's adopting it.
Yeah. All right. So I think we have to stop now. It's more than 1 hour. So thank you very much again, Prof. Taufik, for the very interesting talk, and I'm sure we have a lot of opportunities for collaborations in the future. And I'm looking forward to that. So right now, I will pass back the session to Prof. Rafiq to close up the session.
Thank you, Dr. Nick Rumzi, for chairing the session and for introducing Professor Taufik to me. And to Professor Taufik all the way from California, thank you so very much. And then I forgot to mention at the start of this session that over there in California, it's 8 p.m. or 9 p.m. in the evening. Yeah, so it is actually not an office hour for you. So really, thank you so very much for spending some of your evening time with us here in Malaysia. We received close to 200 live unique viewers. So it is an interesting topic with lots of live viewers. And I believe that afterwards, those who could not watch this live session will watch it afterwards. And inshallah, we will receive another a couple of thousand viewers for your lecture. It's certainly interesting because I'm not an electrical engineer myself, but the way you explain, in layman's term, makes me feel that we used to take things for granted, about our smartphones, our LEDs, our light bulbs, now I'm using Mac with USBC, So this is an interesting lecture, and I believe that it relates directly to all of us, the non-electrical engineer. So interesting topic. And but I guess the most interesting slide is where you show the location of Cal Poly in San Luis Obispo. Yeah. Right. I can't wait to be there and meet you in person, inshallah.
Waiting for you.
Yeah. All right. Again.
And by the way, Prof. Taufik, you are always welcome here, anytime.
Absolutely, yeah. Hopefully, when this pandemic is over, I'll make a plan to visit. Absolutely.
Excellent. Thank you so much, Prof. Nick Rumzi. Thank you so much, Prof. Taufik. And thank you so very much to all our viewers around the globe. Thank you for watching. Don't forget to share, comment, like, and follow our Facebook. Inshallah, we will have many more distinguished lectures for you. Up until now, Until then, bye for now. Thank you.
Thank you. Pleasure.
Bye.
It's a pleasure. Thank you.